Okay. All right. Hi, everyone. I'm Brandon Ong, and I'll be covering convolutional neural networks. Um, okay. Sorry, there was a bit of an echo. Okay. So first, I'll just give an overview of neural networks. Landon explained this pretty well, so I'll try to kind of go over this pretty quickly. So the basic idea is that this is a computer system that is designed after the human brain. It's designed to kind of replicate how we as humans recognize things and then transfer that to a digital computer. So in the in a neural network, there are nodes which represent the neurons in our brain, and then the connections in between the nodes, these wires over here, those represent the synapses. And then kind of it's like a chain reaction from the input all the way to the output. And then you'll have these layers in between, which Lynn already discussed, and those basically kind of after you go through each layer, there's more and more detail that you're able to discover until finally the network can guess what it's actually deciphering and give a probability of how likely it is correct. All right, so this is the basic equation for how each node gets its value on the right over here. So on the left, these nodes on the left, they represent each data point. So for example, if you had an image, you would have a node on the left for every single pixel. And then you would have a connection to every node in the next layer, and so on. So the way the value is assigned, for example, for B1 here, is you add up the weights times the value of the previous node. You add up all of these connections, and then you subtract a bias, and then you input that into the sigmoid function. So basically the sigmoid function, it takes the value and then translates it from 0 to 1. And so that just makes it so that if you have some insignificant data, something it doesn't progress throughout the neural network. All right, and then you can adjust the bias to say if you want a value higher than 4 to go through, then you would put 4 for the bias. All right. So the convolution neural network, it kind of builds off of the basic neural networks. So if you can see on the right over here, this is kind of the flattened neural networks that you've seen before from Landon. And what's great about convolutional neural networks is it's able to reduce the size of the input while still keeping track of features. So this is really helpful for image, just processing through images, because, for example, I'll go to the previous slide. If you have 4K resolution, you'll have about 8 million pixels. So you'll have 8 million nodes to start with, and then you'll have a connection that is 8 million times the amount of layers next, and it just keeps on going. So that is a lot to process. So the purpose of the convolution system is to just reduce the size of the inputs to make it achievable, so it's not overwhelming for your system, so it saves a lot of processing power. So first, you go through the convolution. Basically, you take a filter and then you slide it across the image until you get all of the pixels on here, and it just makes it a bit smaller, but it's able to detect features on it and have spatial dependencies, so you can see like you'd be able to see edges and stuff like that. And you can actually adjust the filter, which I'll show you later. And then after you do that, there's a pooling layer, which basically it takes the image and then it shrinks it down. So it's basically, I like to think of it as an image with less resolution, that you still have the same, it still looks the same, it's just less pixels. And you can continue convolving and doing the pooling layer until you have it at an input that is acceptable for the neural network. Okay, So here are some quick examples of the ways it's being applied nowadays. So the first one is image recognition. I've seen this, like, for example, on Google. If you have an image, you can ask, Google can say, this is what I think it is. So if it's a person, you can say it's a person holding a cat or something like that. So you're able to take an image and kind of categorize what is this with pretty good accuracy. The next one is a self-driving car. Landon kind of already talked about this, but it's really helpful to do convolution with it because it just speeds up the process, allows you to use less, and it helps with just doing stuff quicker. And then the last application I have here is facial recognition. It's really good. Again, you can detect the edges. You can detect the main features of someone's face very quickly. Okay, so now I'm going to go into specifics of how does it actually work? What actually happens in the convolution process? So this is just an example. If you have a 5x5 image, you'll have the pixel values, and then you'll have a filter that'll be a bit smaller than the image. So the values within the filter, they can be changed to have different results. You can have, for example, if you have a colored picture, you can have 3 filters, one for R, one for G, one for B, to further decipher it there. So as you can see in this GIF here, the filter will slide through the image, going through all of the pixels until you have a smaller feature here that's able to, it's just a little bit more compressed. And the way it works is you just do a convolution. So for this example, when the filter is on the top left here, you just multiply the overlapping pixels and then add them all together, and that's how you get this. So for example, there's a 1 at the top left, and then a 0, and then a 1 both here. So that's 2, and then 0, 1, that's 3, and then finally you have at the bottom corner, you have the 4th, and then so that's a 4 here, and then you just do that all the way through the image. And then if you look at these pictures to the right, you can see how adjusting the filter will get you different results. So you can look for different things. So for example, this first one is just a mirror image. It's the same. But then with the edge detection, you're able to really see some interesting features. And then you can also sharpen the image, blur it out. You can do a bunch of different things. All right. So next is the pooling layer. So this is just really helpful for compressing the image. You can take a group of pixels and then narrow them down to just one, and it just really helps a lot. So there's 2 ways of doing that. There's max pooling and average pooling. And well, I guess there's another sum pooling. So max pooling is very good for noise suppression. If there's a value in this block that's more than it should, it'll be kind of eliminated because you only take the greatest one. So you look in the block, you take the greatest, and then you put it in the result. Although if there's a big outlier, then that'll obviously go through, so that's not ideal, so there's a drawback. And then average pooling, obviously you just add up all the numbers in here, and then you take the average. So it's a very good representation of what's there. And then on the right here, you can see an example of what it looks like. You can see some features going through. It's a little bit hard for us to see, but this is just the ways of the results of different types of pooling. Okay, so now that we know about the convolutional neural network, we can talk about how to train it. So it's pretty similar to just a normal neural network. So first, you will just randomize the filters and the weights, and then you take a training image and you feed it through, and then see what the output is. Now, obviously, since the weights and the filters are random, it's going to be completely wrong. So then you calculate the total error with this little equation down here. And then with that, you use back propagation to calculate the gradients of the error, and then that'll update the filter, the values inside the filter, the weights, and the biases within the nodes. And then after that, you'll just repeat with other images until it's able to be accurate the majority of the time. Okay, so here I have a demo that's actually really helpful for visualizing what's actually happening here. So this is a great example. You can draw a number and it'll decide what you have, what you've drawn. So for example, I'll draw a 2. Okay, so you can see exactly what each layer does. So at the bottom here, you have the input, and then it shows the convolution through the filter. So you can see there were 6 different filters, and you can see what they do. For example, this one is really good at detecting almost horizontal edges, and then this one is good at detecting vertical edges. And you can see as I go through and slide it, you can see how it's sliding through the image, each value. Okay. And then after that, you have the pooling layer. And you can kind of see the top and bottom, the pooling layer and convolution layer, they're very similar. It's just this one has less information. It's not quite as detailed, but it still conveys basically the same information. Okay, and then you go through another convolution layer. And so it just creates, it's even smaller, but still has the same features. And then finally, you do another pooling layer that it makes it much smaller. So it goes from quite a large image to something that's very manageable. And then finally, you flatten it. And then so this part right here is the neural network. And then it is able to determine that I actually drew a 2. And so if you look here, you can see that each node is connected to every single node before. So this would be just an enormous amount of connections if we did not reduce the size of it. And finally, it goes to the 2. And then you can kind of see how it works. For example, if there's a loop at the top, then it'll think it's either like a 7, 8, or 9. And then from there, you can it can go even further. So I think that's just a really good way to visualize what is actually happening. All right. And then I'll go ahead and open it up to questions.
Let's open up for questions. Yeah.